So good afternoon everyone. We will start today's session within a few minutes. Okay. So we'll start. So first of all, I welcome all of you to this live interacting session, which is our eighth live interacting session on this course, this conduction and convection heat transfer. So you have already gone through this fundamental concept of conduction and convection, and you have gone through the lecture provided by Professor Chakraborty and Professor Shum, right? So I am here as your TA for these courses, and I will be dealing with this live interacting session where I will help you to solve numerical problem based on the fundamental. So my approach would be to go through the fundamental, like how this thing is coming and how it will help you to implement in the numerical solution. That thing we will do here. Okay. So so before going into this numerical, let me introduce about these courses to you. So why this course is important? This course, conduction and convection heat transfer, is important because in your daily life, if you think about a problem, say a real life problem, a water is flowing, or in a water is flowing over a plate and over a pipe, and if the temperature of the atmospheric temperature is quite high, so what will happen, the pipe gets heat up. So as because of this, the temperature of the water inside it will increase, right? So this phenomena these phenomena we will study how we will solve such types of problem. That is quite important if you understand this concept of conduction and convection heat transfer. Though radiation is also a mode of heat transfer, but we will not count this thing here in this courses. So if some of you may enroll for these courses, so please go through each and every lecture. Try to understand the fundamental, not like you got a question and you have to solve the numerical, like not like that. You just try to understand the basics motto of why we are using this equation and how to implement it. In the question, maybe sometimes the condition they can change, but if you go through the regular procedure, that then sometimes it is not possible to solve the question, right? So it is my suggestion that please understand this thing in a proper way. If you have any doubt, please raise your concern to me. Okay. So in the last class, we have mainly deal with this conservation equation. Basically, we have been dealing with this first continuity equation. Then we have discussed with this momentum equation. Okay. So So in this session, our main motto is that we will discuss about this energy conservation equation, and we will try to have this discussion on this thermal boundary layer based on this energy conservation equation, and if time abates we will also go into this energy integral equation. Okay, just a minute. So in the last class, if you recall, I have discussed about this Reynolds transport theorem. So I will start with this Reynolds transport theorem because I have told that if you know the Reynolds transport equation, you can easily derive this continuity equation and the momentum equation. So I am recapping some of the fundamental things, not the full derivation. So the main motto is that just you need to know the step, simple step, which is quite essential. Like if I talk about this Reynolds transport theorem, what this equation state, the equation state that if n is a property at any certain properties in a system, so then it should be equal to the rate of its change in a control volume plus in a control surface, what is its flow rate. So basically like that we have discussed. So this is your into dA. Like so this is the Reynolds transfer theorem we have discussed. So if this is a system, so if I talk about this small, which is your control volume, in the control volume, how much, see rho into volume means this is mass. So how much mass is entering into change of mass in this system, in this control volume, that is counted for this term, right? And for the control surface, say in the surface, if something, if in this system, if some liquid is entering and some liquid is going out, so that thing is related through this term. That's why it is correlated with the CS, which is the control surface. So a surface term is there and a control volume term is there. Also in the last classes we have discussed how to convert this control surface into control volume. So that methodology is known as your Eulerian method. So we have discussed about this Lagrangian approach and this Eulerian approach. So what this approach was basically, so I am just giving you the same example. Like if I talk about if in a river, you see that that leaves are flowing in the river. So if your main motto is to only focus on this leap, so after a certain times this position of the leap will go changing. So your focus is important. If the focus is leap, then at that certain moment it is known as Lagrangian approach. And say if your focus is just to focus on a certain position in the river, say if this is the river, if your focus is only this region, then your target is that whatever is be flowing through this region, you should deal into it. Say bottle can flow through it, a leaf can flow through it, and wooden block can flow through it. So all these things can be coming in under your observation. So that is an Eulerian approach. Okay. So so basically in our study of the thermal or this convection mode, we are be dealing with this fluid and the convection. So for this reason, our main motto is that we have to deal with the Eulerian approach. Like, so we have deal with this first. We have talked about this continuity equation, right? So in this continuity equation, what is our assumption? Our assumption basically was n. N is basically mass, right? So what is small n? Small n is basically per unit mass, which is 1. So if I put this thing, I eventually get a term. Can I write the full whole equation? So which is basically equal to 0. So this is the equation I have got. So if someone say it is in a steady state, what is steady state? Steady state basically the change of a property with respect of time should be 0. So if it is saying that it is a steady state, then this thing will be 0. Or sometime it may say that the fluid is incompressible. In that case also it is 0 because the density will not change. So our main target is this term, right? So maybe some of you is confusing about this gradient, about this divergence term. So what basically this thing is, so if I consider, if I, let me write this thing, if I expand this thing, so I will get rho. Rho is a, and what is v? V is the velocity in the x direction which we consider as u. Similarly, I can take the this one in the y direction which is v, and so this is how we have to elaborate this thing, right? So what I am saying that if the fluid is incompressible, then this term should be 0. Or another important thing, this whole term is also known as total derivative. Sometimes you see that this whole term we can write this as this form. So just a minute. If you see that these types of thing or capital D is there, that means it's a total derivative, which indicate that there should be the first term is a partial derivative of the function with respect to t, and rest should be spatial or the space distribution. Got it? So here that basically indicate this is del rho del t. Say in this term, if I talk about this term, you have in the integration derivative, you know that one term will be like d dx of u plus u d rho du, right? So if it is a, if I talk about, if it is a compressible sorry, if it is an incompressible fluid, so in that cases you can eliminate some terms. So which term you can eliminate? Can anyone tell? If it is a incompressible fluid, which term you can eliminate? Anyone? So if it is an incompressible term, then you can eliminate this term because it's a rate of change of density. So there should be no changes in density, right? So that's why I'm just writing this thing in a different way for your understanding. Say df dt. Basically, this means if somewhere this thing is written, it basically indicate. Okay, that is the these are the thing. So that is not right now, it is not required that much. I hope that you got it. Similarly, in the conservation of momentum equation, what we have, we basically here we consider n as a momentum which is dm into velocity, right? And similarly, your n should be only velocity because it is per unit mass, right? And the final equation which you got, what is the final equation you got? So I have the final equation. Just a minute. So d dt of rho ui plus j. J is another direction. Say I is, if it is in x direction, then it is in y direction, like that way. So such certain types of equation you have got. So it is not necessary right now. Just you, why I am saying this thing, because if you know this thing from where this equation is deriving, that is essential. Okay. So now I am moving to this energy equation, right? My main motto is the energy equation right now. So for this energy equation, I am erasing all these things. So I think anyone has some doubt. Let me check. So you can raise, whosoever has doubt, please open your mic and you can raise your concern. Anyone? Let me check. Please say. What is your name? Katika. Please raise your concern. So you have raised your hand. Any doubts? Okay. I hope that by mistake you have raised it. So whosoever have any doubt, he can on his mic and raise his concern. So the next thing is that we have to derive this energy equation. I am not deriving this energy equation in full, just I am showing you the fundamental step because it is necessary to understand or to solve numerical problem. So this is your conservation of energy. So again similarly from this RTT equation we have to start what this RTT equation state, that is dn dt, this of a system should be You remember this equation? Rho n plus Cs rho e Vr into n into dA. Okay. So for the energy conservation equation, our n should be energy. So small n should be energy by mass, which is basically small e. I represented it as small e. So now we just assume that it's a control volume. So the control volume is stationary. We just consider this control volume is stationary and not deformable. It is not deformable. So from this equation, what I can write? So from this equation, can I write dE dt of system? There should be Cv rho e plus Cs. Sorry, this is your n rho e Vr into n. So one thing, please remember. So what is Vr? Velocity. This is the R represent the relative velocity. As we have considered this control volume as stationary, so what may be the relative velocity and the original velocity? They should be same. So we can also represent it as V, not necessary to be represented by Vr, right? Now I am talking about this first law of thermodynamics. Say this is a system. So in this system, so I have to check this energy, rate of change of energy in the system. So basically from this first law of thermodynamics, what I have, so if you are supplying an energy Q in a system and the work done by the system is W, so I can correctly write it as Q dot this heat flux is equal to net energy change in the system plus work done. Okay, so in that place now I can represent it as Q minus W. Again we know that, just a minute for your better understanding, we also know that since it is a stationary, so we can take the derivative inside it, right? So that's why I can write it as this way. Similarly, this control surface, as it is an Eulerian approach, so we can convert it into a control volume. For this you need this divergence term, right? Is it clear? This into, so this is the term. So now in this equation, up to this I hope that it is clear. It is control volume, it is control volume. Right. So now you have to deal with this Q. What is Q? Q is the heat. So basically, in the last derivation of this momentum, we have considered force, two types of force. One is body force and another is surface force. So similarly here, the heat we are talking about, we just categorize it into two types. One is the space heat flux and the volumetric heat. So these are so I have to integrate it with S2 volume. As I am talking about only a small portion, which is a control volume. So this is integrated somewhere, right? And now is there, which is your heat flux. So the heat is surface, so the heat flux. this Q dash is a surface. So I have to write this with respect to there should be an vector n vector like this one into dA. Okay. So this heat flux, say this is the Q. So because of this Q, there is a heat generation here, and the heat flux, the heat is moving out, so which is Q dash. So for understanding purpose, I can represent it as minus. So it is not necessary. This is because of the sign convention. Like in this first law of thermodynamics, we take whatever be the heat entering the system as positive. So that's why the heat that is going out, we just consider it as negative. So the inverse configuration you can choose. I am talking about the symbol configuration. Okay. So now you again see this is in the volume terms and this is the area term. So again I can convert it into this control volume term. So if I have to convert it into this control volume term, so there should be a divergent property I have to use. So if I use this divergent property, there should be your Q dash. Okay. So this is say this term is in control volume, control volume. Again we have got the Q in control volume term, right? Similarly, if I talk about this work, so what is the work? Work is also consists of two terms, which is the surface work done, and this next is the body work done because of this body force. So surface force basically it is the shear term we have talked about in the earlier classes. So this shear term, if I talk about, this is tau ui into area I need to take. Okay, into n cap is there. This is in the contour surface property, so it is should be in CS, and the control volume term is there, which is your body force. So this is Bi into. So accordingly, we have to control this control volume, control surface into control volume. So I will get this term. Okay, just a minute. Small silly mistake is there. So this is your V. So this is this thing I can write tau V into dV, this is your control volume term, plus, okay. So see, each and every term we have converted into this control volume term, right? So up to this, see, check this thing and let me know that if you have any confusion. Else we will move into this, into the next part. Anyone, any confusion? Okay. So after all these derivation, these integration terms will go out, and after eventually, after that, if we split derivative this thing, what we will eventually get? We will eventually get a form of equation. I'm just writing the final form of equation, right? This is your rho dE dt plus u j. That means here, previously it was a vector. Now we just split it into component. This is your this term. This is the heat flux term. We have talked about the first is the heat generation term. This is the heat flux term. Plus we have also talked about the shear stress term, which is your tau xj. This is uj plus b I uy. See, if you talk about this thing dE dt. So from where this thing comes? This comes from this part. Rho dE dt. First thing you got. Sorry. So this is the first term we have got from here. Okay. So now I am coming to the next term. So next is your derivative with respect to v and a. So it should be derivative of uv. So one term will be, first you will come out derivative of v with respect to, this is gradient term with respect to x or y or z. So that's why if so I have represented it as x j cap. This is index. Index basically, like I can talk about I is 1 2 3, j is 1 2 3, like that. So if there is two axes, so x will be 1 x1 and x2. X1 is the x axis and y1 y2 x2 is the y axis, like that way. So this is a simplified form to represent this thing. I think you got it. Okay. Just a minute. One little step I have done. This is UI. So this is the final form of the equation. Now this is in terms of energy. So also from this Navier-Stokes equation, which we have already discussed, if I apply this Navier equation here, so what will I get? I can write this equation in terms of this your internal energy equation. So I am writing this equation in the form of internal energy. So if you write it in terms of the internal energy, I am just writing it the only the equation, because Already this thing has been derived in detail in the class by Professor Chakraborty. So I am just explaining it for you in short. Okay, there is a bracket here. Sorry. Hmm. So in place of E, I just replace it with I, internal energy. So total energy basically consists of your kinetic energy, and the internal energy, and potential energy is also there. But see, we have only included this BIUI term, which is your body force. That means this potential term. So in this U, we will not count this potential term. We will count only the kinetic energy term and the internal energy term. So see, this is your energy equation 1. So from the Navier-Stokes equation basically consider U velocity. Yeah, so basically from this Navier-Stokes equation you can get this velocity term. So which correlates with this kinetic energy. U correlate with kinetic energy, right? So this energy term minus kinetic energy, what is the energy remaining? It is the internal energy. So that's why this term is coming. Uj Uj di, I is the internal energy, x j equal to q double dash minus. So this and only this body term will cancel out. So you will get only this types of equation. E- This is your T I j and del ui del x. After this equation, a little bit after 5 or 10 minutes, we will discuss about some numerical problem based on this equation, how this thing is derived and all these things. So this is the final form of the equation. So any confusion up to this, please let me know. Okay, this thing I have forgotten to do. This is J. This is also J. So this is your final form of the equation. So now it is important to understand what this equation indicates. Say why to understand this equation important. This equation, the first term is your transient term because it is the rate of change with respect to time. So it is the transient term. And overall this term I can say that if this is the convective term and this is the advective term, right? So this is the total energy change term, right? And the Q is the your energy generation, where this one is the heat flux surface term, and this is your stress in a fluid phase, stress term in a fluid fluid. Why this is required? Stresses in a fluid phase. Because this is like the tau is a shear stress. Shear stress basically means there is a friction. I can say that there is a impact between two layer. If a fluid is moving, that means a layer, one layer, the bottom layer, the top layer is moving above the bottom layer like that. So if a layer is moving over another layer, what will happen? There is some friction generation. So if you talk about you rubbing your hand, if you rub your hand, there will be heat generation. So similarly, these terms also account for heat generate, account for this heat input. So this is your viscous dissipation. So because of the viscosity in a fluid, whatever will be the heat generated there, that is converted into this equation. Okay, so all this term is important. These three term, one is the heat generation into the volume, into a specific volume. Next is the surface heat flux, and third is the because of the viscosity. So three term basically is there. Please remember this thing. Viscous dissipation. So there is three terms we have considered, right? So in the last classes we have talked about the Stokes hypothesis, right? So I am not deriving this Stokes hypothesis again. So again, if I just write it directly, Stokes hypothesis, so you will get a term like this way. This term, I am talking about this term. I am talking about. So from the Stokes hypothesis, what you will get? You will get this term, which is your minus P. So many of you may get confused why there is ij and why there is k. So that thing you may get confused. So no need to get confused. So ij basically means if it is 1, then it shouldn't be 1. Generally, if I and j are not equal. So if it is 1, it is 2. Like that term. So if it is 1 means it is in u direction, then it should be in y direction. Similarly, if it is v, it is dz. Like this way, this term represent. But this term uk and xk and del uk xk, that means this is the total term, del u by del x plus del v by del y. So that is the velocity gradient in that direction in which the velocity vector is there. So that is the difference, right? So this is the thing. So from this term, what I will get? I will get basically two important things. This term, which I call as the shear stress term, it consists of two terms. One is the hydrodynamic term. Next is the viscous distribution term. So basically two term. Our main target is this term, viscous distribution. Because this hydrodynamic term, though it is there, we will ignore this thing. So our main term is to study about this viscous term. Our main motive is the heat generation, surface heat flux, and viscous dissipation. Why viscous dissipation? Say up to the concept you have learned, what you understand. So you understand two important things. One thing is that the first is that you understand the temperature gradient in case of your conduction, right? Similarly, if I talk about the fluid flow, you have studied about the velocity gradient, which is correlated with this viscosity term. So that's why viscous dissipation is important, and heat flux is there because you studied about the conduction and convection. So from that it can be counted, and heat flux they can provide, and if not provide we will assume zero. So that's why this thing is essential, right? So now if you put it here, okay, so you will get a term. Is there any mistake I have done? I think no. Okay, so that is the thing. So up to this it is okay. Now just I am just putting another important thing. Say this H. So now if you use this H, is the enthalpy as a function of P by rho. which basically comes from H is equal to U plus PV. So this is in the, you have got H equal to U plus PV. This is the same thing from the same thing. This is another terminology where H is the per unit mass, enthalpy per unit mass term. So if you use it, all these things, so you will get an equation. Final equation I am just writing. So after, before this, whatever you have studied, no need to recall this thing. So it is a quite interesting thing. Just if you remember this thing, that would be sufficient. So basically, there is two form of equation. This equation I am talking about here. Okay. So this is the, what is dh, capital D. This is your total derivative. So the total derivative term basically means here, total derivative term. Say if it is df by dt. Again I am writing. So this is basically your df dt plus your u uj df dxj. So that is your partial derivative term. Okay. So that is your df term here. Any confusion up to this? Please let me know. That means you can directly say that if it is in x direction, this is small u, this is x. If it is in y direction, because j and j, that means both are same direction. It is v and it is y. If it is w, it should be z. So like this way. Okay. So that is the term. So this term is there, but most often in the, as it is talking about the energy equation. So whenever there is energy, we always depends on this temperature term. So now I am just writing it in terms of the temperature term. So based on which it is now necessary. This is the energy conservation equation, very important equation. So whatever I have explained earlier, so this is the just a step to solve this thing. So you know that in case of this temperature profile, enthalpy is the, if there is enthalpy, so you can correlate this enthalpy into temperature, pressure, or entropy, because you have studied about this in thermodynamics. You have studied about this Maxwell law. From there, you know that if enthalpy is a function of time and pressure, then how you can write it. So this thing, you know. Similarly, if the enthalpy is a function of temperature and entropy, then you can also write it. So based on your requirement, you have to write. But in majority of the scenario, if I talk about in this particular course, so we will be starting with the temperature in case whether it is your convection or conduction. Mainly our target is to study the temperature. Most of the question or numerical, what you try to find out, you try to find out any temperature at a specific position, or liquid temperature or solid temperature, like this way. So that's why this energy equation eventually we have derived in terms of the temperature. Okay, just a minute. So now the important thing. Yes. Hmm. So this is the final form of the equation we have got from the temperature profile. Now I'm just moving to some numerical question. So I hope that after this you will easily able to understand this thing. So the first question is that the equation which already I have explained. So this is the thing. So before starting this, let me discuss about this term a little bit more. So I have already told you that this is a what is Q dash? Q dash is the heat flux, right? So if it is in heat flux, so heat flux how you will put, if it is a convection you know how to put it, and if it is a conduction you know that is the K dt by dx. So accordingly you can put, right? So this is your viscous dissipation term, and this is your compressibility term. So in most of the cases, this compressibility term we ignore this term, or it can be neglected in our scenario. Even this viscous dissipation term we most often disregard this term. So basically in this equation, if you look into our main target is this first term. Okay, so this is your transient term. Rho Cp, if I talk about only rho Cp is the energy storage capacity of any thermal system. It is talking about here. And Q dash is the heat generation. It may sometimes be given, it may not given. So basically, in most of the question, you should target this term and this term only. So rest other term is not that much important in many numerical question. Only these two terms is basically required. So this thing basically you have already got from this 1D conduction equation. So this is the same thing you have got. Rho Cp dt by del T, capital T by del T equal to minus uh, K del square T, like this. So this is the same thing. And heat generation term is also there. And say this minus term, it may be confusing to you that there is a minus term. Because say this heat flux, this heat flux basically, in this heat flux, if I apply this Fourier trans equation, so which is that Q equal to minus K del T by del X. So accordingly you can put, no, sorry, minus K del T by del X. So you can easily put, so minus minus will give you a positive response here. So ultimately in ultimately this is the approach you should follow. So this compressibility term and this viscous dissipation term, though it's a part of this energy conservation equation, but in majority of the scenario we will discard it. So now I am again another thing. These terms. So this term basically is why I am repeating this thing, because this term is quite essential. Uj del t by del xj. That means if there is it is a 3D coordinate, so then it should be u. It is same thing plus this should be v, like this way. Okay. So see, this is your total derivative term or material derivative term. So remember this thing. So please coming to this first question. So the equation is given, and in this question it is said that if the left hand side of the equation one, rho Cp can come out of the derivative because they are assumed to be constant for this particular derivative. State true or false. Please try to answer. Anyone? Please try to answer this question. I am giving you 1 minute to think. See, the correct answer here is I haven't got any response. So the first thing in the it is talking about the left hand side. The left hand side of the equation has to come out of the derivative because they are assumed to be going to for this particular derivation. So no, it is not the case. Why? Because already I have talked about this rho Cp. What is rho Cp? This is the energy storage capacity of the system, right? So in the derivation, if you remember this thing, if you remember this thing, this Cp. So we also know that Cp is not Hindi here. I just write. So if you remember this thing, the Cp basically is dH dt. Yes or no? So this is basically your Cp. The rate of change of enthalpy with respect to time basically is Cp. So the Cp is not constant because already this equation has been derived from this thing. I have told you that this derived from this thing, as this CP depends on age and derivative of it. So how can we say that it can be constant? That's why the correct answer is option B. It's a false. Okay. So similarly, next question. So the energy equation for the convection is derived keeping in mind the following condition. So these are the option it is given. So please try to do. I'm just writing the equation again. Maybe you will forget this equation. Okay, so this is the equation. So in this question, in this equation for this convection is derived keeping in mind the condition of the fluid flow, but still we use this Fourier's law of heat conduction to describe the heat flux term. Of the statement 2 is the conduction is a fundamental mode of heat transfer and not convection. So again, I am giving you 1 minute time to respond to this. Hmm. So still anyone? Okay. So see this Q term. If I talk about this Q term, this is the heat flux, right? So say that in the heat flux condition, the energy equation for the is derived keeping in mind the condition of the fluid flow. So first thing is that I have earlier told you in the first few classes that there is basically two fundamental mode of heat transfer. This is conduction and radiation. And okay, this is conduction and radiation are the fundamental mode of heat transfer, right? But in these cases, this convection, if I talk about this convection, convection is not a fundamental mode of heat transfer. It is basically conduction plus fluid flow. If I take, if there is fluid flow and conduction both is taking place, then this phenomenon is known as convection, I can say. So that's why it is not a fundamental mode of heat transfer. So statement 2 is correct, right? So now, if I talk about this equation 1 for this convection, so it is saying that we can still use Fourier's law for convection. Why not? So say if there is a metal plate, right? In this metal plate, if you know the temper, whatever may be the heat flow because of the convection, because of the conduction, it should be equal to because of convection, right? If this is T infinity and H is there and it is T surface, it is T1. So you can calculate this heat flux from this conduction and also the mm, heat flux because of the convection. So if you equal both these, then you will get the value. This should be equal, I can say. So whatever should be the heat flux because of the convection and what should be the heat flux because of the conduction, that should be equal, right? So now in this equation, say if I talk about this equation, here this Qj I can write it as minus K del T by, I can write, if I can put it in terms of conduction, and if I have to put it in terms of convection, then how I have to put, this is minus H into T minus T infinity. So this T I can also write as del T or change in T. So you can also put, accordingly you can get. So that's why option statement 1 is also correct, statement 2 is also correct. But in this option, say the statement 1 is 2 and statement 2 is 2. But statement 2 is not a correct explanation of statement 1. No, it is not the correct. Because statement 2 is the correct explanation of statement 1. Was already say that this thing, from this thing what I say, that this conduction, that the heat transfer because of the convection is because of this conduction phenomena. So indirectly this convection is related to this conduction. So that's why option B is the correct answer. So any confusion up to this? Okay, so I'm moving to the next question. So please try to answer this thing because I have explained this thing a little bit ago. So it is talking about these terms. So I say that these terms these are the some of the term which we basically neglected in your current course. So Katika, can you please answer? Avinash, Katika and Avinash, right? So no one is there to answer. Let me check who are in the call. Okay. So see, in the as I have discussed in earlier slide, these terms in this question they are talking about this term. This term basically is a compressibility or because of flow work which we will neglect, right? So the question is simple, what this term represent. So this term represent flow work, it is correct. This term can be neglected for flow with negligible compressible effect. Compressible basically this term. If this beta is less or negligible, then this whole term should be negligible. Say the value of beta is tends to 0, say 0.001. In that case, whatever you multiply with this thing, that should be coming around is quite less, is very, very less. So that's why option B is also correct. So the main correct option is of both A and B is correct. It's option C. In another word, negligible, if I talk about this Negligible compressibility effect, which basically also means incompressible fluid, almost incompressible, right? So if it is not incompressible, then basically you can also say that the total uh, derivative term of this P will be, or that is the pressure term, will be zero, almost zero. So this is the next question. So the convection can be explained as the advection resistant conduction. Is it true or false? So advection basically means the energy transfer because of the fluid motion. I am giving you hint. Advection basically means fluid flow or fluid motion. So think, let me know which will be the answer. So see, this is the correct answer is true. Why it is true? This is because I have already told that this conduction and this radiation are the fundamental mode of heat transfer, right? Or the main mode of the heat transfer. Like I have said in the earlier here. Okay. So this is the fundamental mechanism is the conduction and the convection. But if you talk about this, hmm, but if you talk about this convection basically even in the first class I have written there. Convection basically is conduction plus fluid motion or fluid flow, which basically means your advection. So convection basically is conduction plus advection. So if you can put those both these two things properly, you can easily do a simulation of this convection. So only conduction is not sufficient for convection. Fluid flow is quite essential, or the advection, which is also known as advection, is essential. So that's why the correct answer is option A, true. In another way, if I can say that if you are applying a heat to a plate and the plate is exposed to water, so the water will definitely get heated up. So how the water will get heat up? It will get heat up because it get heat from the heater or from this source, right? The next question from this equation, and this is the last question. Hmm. So see, try to answer this one. It is an important question. So I'm just giving you 1 minute time to think and answer. Hmm. So anyone? So see, this is the question is that deriving the equation one, which is the equation in terms of the temperature. So the first internal energy is expressed in terms of entropy and then entropy in terms of temperature. So they have asked whether first you have expressed in terms of entropy and then temperature. Next option is that in terms of enthalpy and then temperature. The third option is that directly in terms of temperature. Fourth option is all of this. So which of these following is wrong? Not correct. It is seventh. Which of the following option is wrong? So see, I am just showing you this thing equation. So see what I have said that initially the equation and internal energy. This is I is internal energy. This internal energy equation is written into enthalpy, right? Enthalpy equation, and then from this enthalpy equation using this Maxwell equation and all these things, you will get the temperature equation in terms of the temperature. So you will definitely use this. So that means the first it is from the internal energy to enthalpy we have convert, and after that enthalpy to temperature. First we have just written this in terms of I. From I we have written it H. From H we have written it to T. So the correct is option A. So, sorry, not A. Option B. Sorry, not A. It is. So the internal energy is first written in terms of enthalpy and then in terms of temperature. So option B is the correct answer. Okay. I hope that you get it. Okay. So now I am moving to some fundamental concept of this thermal boundary layer. So this energy conservation equation is over. So that's why I am saying that please derivation, if you recall the derivation it is good, but try to understand the step. What are the step you do first? Like that first there is the from the RTT equation we just assume this thing, what thing? We just assume the value of n, and after that we have to use the thermodynamic first law. From the thermodynamic first law we have to define this q and w. So this q we have to all this in all this term, if there is some term in terms of this control surface, we have to replace it in terms of control volume. These are the initial step, right? So after that we have to use the stroke equation. From the stroke equation we can summarize it in short, and after and also we have to use this Navier equation, and ultimately we will get this equation in terms of your, which in terms of what, in terms of your internal energy. Then this internal energy is getting converted in terms of enthalpy, which is a thermodynamic things, and from this enthalpy we require the temperature, so we have also converted it into temperature. Okay, so the condition is that from from internal energy to enthalpy to temperature. So the question is that now we will discuss about this boundary layer. Thermal, though there are in the fluid mechanics you have studied about this boundary layer. Now in thermal you will again study about this boundary layer. So what is the difference between the boundary layer because of the fluid flow and because of the heat transfer, right? So both these boundary layer, so they are basically, if I talk about two types of boundary layer. So boundary layer basically forms when a fluid flows over a solid surface. When there is a fluid and if it flows over a solid surface, uh, if this is a solid surface, okay, if a fluid is flowing over this surface, so what will happen? Near the heated surface, this heated surface, this temperature, I am talking about this liquid near the heated surface is affected because of two reasons. One is your viscous force and another is thermal diffusion. Two is because of heat transfer. Heat transport or heat transfer. Okay. So these are the things. Because of this viscous force and the heat transfer, generally what will happen if there is viscous force or if there is heat transfer, there is a thin region developed near the wall. Okay. So this thin layer is known as boundary layer. So in this thin layer, what will happen? Either this velocity will change rapidly or this temperature will change rapidly. So that's why it is distinguished into two categories. One is hydrodynamic boundary layer, another is thermal boundary layer. Hydrodynamic boundary layer, which is basically because of your viscous force. Next is your thermal boundary layer, which is because of your heat transfer. Okay. So this is the main things about this boundary layer. Now I am giving it in detail about this thing. So we'll come to this hydrodynamic boundary layer. So you just remember that two boundary layer. One is because of the fluid flow or the viscous force. The next is because of the temperature gradient or because of the heat transfer. So in these courses we require both of them. Both are quite essential. If we talk about this only in fluid mechanics, so in fluid mechanics, if you understand this hydrodynamic boundary layer, that is sufficient. So what happens in this hydrodynamic boundary layer? Say this is a plate. Please look into this thing. It is quite important. If this is a plate, so this is your U infinity. So if a fluid is flowing over this flat surface or over this surface, what will happen? The the velocity at this region, in this region, but just at the mm, surface of contact of the liquid and the solid is zero, and that condition is known as no slip boundary condition. So see, it is almost like this way. Okay. So what will happen if at this point it is like this way? This types of profile is there. So at this point, if it is zero, then one, 2, 3, 4, 5, 6, 7, 8, 9, like that. There is so many vector. So what we have observed is that this thermal boundary layer up to it reaches 99% of UF. At this point, if it is 99% of UF, you can draw a layer above it. Similarly, Similarly, on increasing the see the fluid is already flowing. So in each and every point with the surface velocity will but as it is continuously moving, so its velocity can rise. So there should be again 99% of should be 99% of surface temperature. Sorry, 99% of ambient temperature. Okay. So in this way you need to understand these things. So after getting this 99, we say in this fluid the U infinity is already you know, but at some point over this fluid this effect is observed. So for that effect we require this. Anyone any confusion up to this? So if I talk about this velocity, if it is zero, it is one, 2, 3, 4, 5, U infinity like that. So near to the approaches, as it approaches to U infinity, at this point we have to draw the, we have to give the uncertainty. Sorry, we have to give the value of this thermal boundary layer, of this hydrodynamic boundary layer. Similarly, it is the way. So the thing is that at a distance, so this is in your y direction. What is the direction here? This is your y direction and this is your x direction. So u in the y direction should be different, right? And for hydrodynamic boundary layer thickness, if I talk about hydrodynamic, Hmm. This hydrodynamic boundary layer thickness. Say I represent it as this way, say delta. So this delta is defined when only when u equal to 0.99, sorry, some issue, 0.99 u infinity and y equal to your this. So meaning that the if the fluid velocity is 99% of the stream velocity at this region, the boundary layer thickness and the boundary layer is forming. So initially, that's why initially the thermal boundary layer is small, and as you move on, the thermal boundary layer is small. And what is the reason behind this hydrodynamic boundary layer? It is because of the viscosity, which causes this momentum diffusion from the wall into the fluid. So that's why this thermodynamic, that's why this, that's why we get this hydrodynamic boundary layer condition. Okay. So this governing equation, just a minute. So this governing equation, if I talk about the governing equation that we have got by solving this energy equation, so we will get this as, okay, so this is how this derivation, so this is the governing equation of this thermal boundary layer equation of this boundary layer flow. U, this is the u direction velocity component, this is the y direction velocity component with y direction velocity component with x direction. Similarly, this equation gives two term. One is the, this equation represents two term, advection of momentum, and next is the diffusion of momentum. Okay. Any confusion up to this? Hmm. So see, as I have talked about this delta, delta depends on what? It depends on the kinetic viscosity. You remember this thing. This delta depends on your function of your, this delta function of your mu. Okay. So if the flow is flowing over the tube having it is in laminar. So if it is laminar, how will you get to know that it is laminar or not? So if it's Reynolds number, based on the Reynolds number, you can say Also, if it is known that its Reynolds number is known, at that case, for this laminar flow over a pipe, what should be the thermal boundary? What should be the hydrodynamic boundary layer thickness? So the hydrodynamic boundary layer is almost equal to x by root Rex. Okay, x by root Rex, and another formula is there which indicates that this equal to minus 5 x by, you got it? Also this thing you can find. So this is how you can find out the layer boundary layer thickness. So I'm just talking about this laminar boundary flow because that is quite essential, and rest are important but that much because already these things are included. So next slide. Now thermal boundary layer. So up to this, whatever I have discussed about this hydrodynamic boundary layer thickness, any confusion up to this? So you understand this thickness, this graph. So basically, if someone talks about this hydrodynamic boundary layer, how can I talk about this? This is basically this heated surface. So this heated surface carries some energy like rho Cp for this. No, sorry. This heated surface have some energy. That energy is transferred into this fluid. For this, what I need? I need this energy. Who will transfer this energy? This energy is transferred by the fluid. So in this region, these are the disturbance region, which basically carry this energy. Okay, these are the disturbance region which basically carry this energy. That's why it is important. Now, if I talk about this thermal boundary layer, say if a boiling surface, if this is a similar things I have drawn. If a fluid is flowing, is a heat, we just apply heat. If a fluid is flowing over the surface, what will happen if this is the surface? If this is the surface temperature at this point, and if this is the fluid, okay. So this is your, say this is your T infinity of the liquid. So it's a common sense that the surface temperature and liquid temperature can't be generally not equal. Say the liquid temperature is 100 degree, then the surface temperature is 100 more than 100 degree because already it has reached the boiling point. So in that standard, I am saying this thing. Okay. So in the thermal boundary layer, what will because this heat from Ts will be transferred to T infinity. How it will be transferred? So for to transfer this Ts into T infinity, you need ATS, right? Sorry, to find out this any point. Talk about at any point. So if you have to find out this temperature profile, so this is how you need to find. Say the same thing I am trying. If at that point if flow is there, say this is flow, not an issue. There is flow, right? say at this point, this is the temperature. So the surface temperature at this point, say it is at liquid temperature is at 30 degree and the surface temperature is at 50 degree. So initially it is 50 degree and then it will try to decrease like this way na. So say this is the point, this is 30 degree, which is T infinity. Okay. So at this point where the T infinity is 0.1% of 1% more than T infinity, like if it is 100 degree and this point should be 101 degree. Okay. So if you plot a curve, this curve should be like this way, right? Similarly, here also, if you plot a curve, it should be coming out like that way. So at this point, if you connect all these points, you will get a curve. So this curve is known as thermal boundary layer. Okay. So similarly, from this energy conservation equation, you will get the boundary layer equation formatted, which is your. I am only talking about 2D, not 3D, which is your alpha rho square T rho y square. Because already the change is in the y direction, so that's why it is in y direction. So this equation basically consists of two terms. One is the advection and another is the diffusion. So see, this is the velocity component. This velocity component is correlated to this advection, and this is your what is alpha. Alpha is thermal diffusivity. So thermal diffusivity basically represent here if there is a certain amount of heat or the storage capacity, thermal storage capacity in a system, it is carrying from somewhere. So in that procedure, how much the how much diffusion or the disturbance is there, that information is provided by this alpha. Okay. So in the previous slide, we have written about this fluid for this hydrodynamic boundary layer. Now we'll talk about this laminar boundary layer, which is X by this one. Okay, so that is it here. So up to this any confusion, so it correlates with Reynolds number and Prandtl number. If I talk in the earlier slide, if it is a hydrodynamic boundary layer, it only deals with the Reynolds number, whereas it involves the Prandtl number. Now the question is, what is Prandtl number, right? Up to this, check and let me know if there is any confusion. So up to this today's lesson, what we have studied in the last two lessons, it is basically deal with the equation, which most of you may find it difficult. But from the next class onward, it's again on the fundamental concept. Though it is also fundamental, but it is mainly depends on this numerical derivation and all these things. If someone of you are not that much good in maths, then it will be tough for you. I know that. But fundamental thing you just understand how to solve this. The approach is just you. If someone tell that you forgot the how to derive this derivation thing, you forgot. So you can just say that from this thing we will got something, and whatever we got from this thing we will apply this Navier equation or this equation or like the boundary, like this way you have to tell. Okay. So what is Prandtl number? Now the question is, what is the Prandtl number? The Prandtl number basically relates two things. Relates hydrodynamic and thermal boundary layer. Okay. So see one thing, in the previous slide, the curve nature is like this way, and in the here also the curve nature is like this, almost similar. So can you say that for a given value of x, x basically means this thing, this is your x. For a given x, is it possible that this thermal boundary layer thickness, this lambda t and lambda both are equal? So that can be a question. In some scenario, maybe the if this is the height of the thermal boundary layer and if this is the height of the hydrodynamic boundary layer, so if both these two are equal, in certain cases, is it possible? So you have to look upon this thing. So for this Prandtl number, so hydrodynamic, if I talk about this hydrodynamic boundary layer, it discuss with this viscosity. So in viscosity, it comes under here kinetic viscosity, which is your rho by mu, right? So this mu by rho, mu means your viscosity, dynamic viscosity, rho is the density. So that means how, what is the what basically is viscosity? Viscosity is resistance or disturbance. So what is the disturbance in a per unit storage? What is density? Density, I can say it as a mass storage capacity. Okay. So in a mass storage capacity, what is the change in the what is the disturbance? That thing is represented by your mu. Okay. In the similarly in the thermal boundary layer, our main parameter I have talked is the alpha, which is thermal diffusivity, which is your K by rho Cp. What is K? K is the thermal conductivity and rho Cp and your rho Cp, which is basically your energy, which is the energy storage, right? So in this energy storage, if I talk about this energy storage, just a minute. So you see these two are analogous to each other, right? In both these things, there is two term. The first is the viscosity, next is the thermal conductivity. So in these cases, if you remember this thing we have discussed earlier in the earlier session, this thing basically means how fast the heat diffuse through a material, right? And if the K is more, so what it indicate? It indicate that the heat will transfer at a faster rate compared to if K is less for a certain material. So it is the ability of a material to conduct by the ability to store heat. It is the ability to conduct heat by heat storage, total heat storage. Okay. So if the thermal conductivity is high, heat spread quickly, the temperature will change very rapidly. Similarly, if the thermal diffusivity is less, it indicates that the heat spread will be less and the material store less amount of heat. Maybe no, I can't say that the material is to less amount of material stored heat, but it depends on the K. Okay. And if I talk about this momentum diffusivity, and this is also known as this term as it is known as your thermal diffusivity. This kinematic is also known as momentum because it is carrying the momentum with the fluid. It is carrying the momentum with the heat is carrying the thermal diffusivity, right? So it measures how quickly the velocity disturbance propagate in the fluid, right? How quickly the velocity disturbance is propagated. So this Prandtl number basically, as I have told, that it relates, it is your delta by delta t. So delta relates to a, so I can say that this is mu by u, right? I can write. So in other word, if you see this thing, you can easily correlate one thing from this thing. So the Prandtl number is equal if its value is 1, so that means at that time if this thermal boundary layer and hydrodynamic boundary layer is equal, then the Prandtl number is 1. So similarly, if the thermal boundary layer is more than the hydrodynamic boundary, then the Prandtl number is less than 1, like that. So that's why it is quite essential to understand this thing. And another important thing that you will study is the concept of this Stanton number, which I will discuss. But before this, we will move into this numerical question. So this is the first question. So what this question state? Any confusion after this? If you do not have confusion, please try to answer this thing. So the question is that if the Prandtl number is 1, so what that means? Already just now I have discussed, right? So it means that both the thermal boundary layer are equal. So the correct answer is option A. Okay. So this next question. So this relates to this Reynolds analogy. So what is Reynolds analogy? That is quite important. Let me recap this thing just a minute. So so we are talking about this Reynolds analogy. So to understand this, first we have to study this a number which is known as Stanton number. So it's a non-dimensional number like that of Prandtl number, Reynolds number. So what it basically represent? It basically represent the heat transfer from a surface by this heat transfer from a surface by thermal energy transport by the fluid flow. So in other term, heat transfer from a surface basically is the H. I can write heat transfer from a surface, basically it is a H, heat transfer coefficient. Similarly, for the thermal energy means rho Cp. As it is clearly it is by the fluid flow, so it should be multiplied with a U. So this is your terminology for this Stanton number, right? So it is basically the convective heat transfer by the energy carried by the fluid flow. In other terms, so this thing is directly related to your Nusselt number. Nusselt number H, the you see that the non-dimensional form of H is Nusselt number, and Reynolds number and Prandtl number, if you multiply, you will get this thing. So how? So you just put the value of Reynolds number, Prandtl number, Nusselt number, you will get this value. So the Stanton number basically is a number that correlate all these things. Nusselt number, Reynolds number and Prandtl number. So now the concept is that Reynolds, now the concept is the Reynolds analog analogy. So it basically relates this your friction or the friction with or the friction with the heat transfer in turbulence flow. So it relates momentum transfer with heat transfer. So basically, how much flow is there and how much heat transfer is going on, that information is given by this analogy, but only in case of in turbulent flow. Generally, here we assume that both the fluid flow, momentum, and the heat transfer are equal. Okay, so it basically represents both the momentum and the heat transfer are equal. So when it will be valid, so for this, the first condition that it should be a turbulent flow. And next is that for the Reynolds analog, so what we need to have? We need to have this nu and your viscosity alpha. This should be equal. That means in other term, we can say that the Prandtl number is almost 1. That can be case. And also as it is equal, then what this this is correlated to your velocity profile and this is correlated to the temperature profile. So both velocity and temperature profile should be equal, almost same, almost similar, right? And from this Reynolds transport, after derivation, you will get a thing from the skin coefficient by 2. The Stanford number is equal to the skin coefficient by 2. That is not required here. Still, I have shown it here. So after, so the correct option here would be, so the question is that which of the following is or are incorrect. So is only high. So it is not correct. High Prandtl, it should be for Prandtl number should be almost 1. So the second option is not here, right? The Reynolds analog is valid. This is correct, and this is not valid for a. So see, it is incorrect is given. So the correct answer is option A, option B, and option C. Okay. So that is how the concept. Huh. So another important thing here, so what I have said that it basically means your convection coefficient and it is your axial heat transfer or this is an axial component. Remember, this is your axial component through because if the flow is through a tube, then the heat transfer is with that flow. So that means it is talking about only this axial direction, right? Now moving to this next question. So the next question is the Stanton number refers to the ratio of what? So right now I have said that it is the convection flux to this advection heat flux or this energy. So convection to advection. Right, next question. So Reynolds analog holds true if so it's a half of the say if the Stanton number is 1 then it should be CF by 2. ST I will get that CF by 2. So which will be the correct answer? The correct answer is if this one will not be the answer, so this one will be the correct answer. Option B is the correct answer. Okay. So now this last question for today's session. So in this question it is said that for a low Prandtl number, if we make the Reynolds number 2 times its initial value, keeping the Prandtl number fixed, the Nusselt number changes by a%. So what is the a value you need to find out? So any idea? So this concept is quite essential. I'm just showing you this concept. Oh, yes. So the thing is that for a row Reynolds number, so the Nusselt number is the heat transfer coefficient. So there is a correlation that Nusselt number basically is a function of Reynolds number root over of Reynolds number or by half into Prandtl number half. This is for low Prandtl number. For high Prandtl number also there is some correlation. So you please go through the book, you will find such types of so many correlation are there. Okay. Maybe in question this value may be given. So this is the thing, it is given in the question also it is given the Prandtl number is fixed. So I can say that this Reynolds number is inversely proportional to, so Nusselt number is inversely proportional to this one, right? So I can write Nusselt number 1 initial case, Nusselt number final by Nusselt number initial, that should be equals to Reynolds number final by Reynolds number initial to the power half. So what is given here? Reynolds number final should be 2 times that of the Reynolds number initial. So it is basically your 2 to the power half. So root 2 is 1.41 like this. Okay. So that is the value. So you say what is the value a%? Russell number increases by a%. So clearly it is visible that this the ratio is 1.41%. That means it is around 41% more. So the correct option is option A. How to find out? Also you can find out the changes, you can find out that is the final changes minus Nusselt number initial by Nusselt number initial. So it can be written as 1.41 by 1, right? So this is 1.41 minus 1 by 1. So 0.41% into 100. So this is on your 41%. So this is how we have to solve this. Okay. Any confusion up to this? So please check and let me know. Else we'll wind up today's session. Any confusion? Katika and Avinash? So I hope that you understand this concept. Okay, Avinash. Thank you for confirming. So see, if you are facing any concern about these courses, you can also raise your concern right now or you can mail to me. So up to this today's session, whatever we have discussed, that is based on the mathematical part of this heat transfer concept. So from the next class onward, we will be dealing with something interesting which will relate with your daily life. So after that, you will get to know how this fundamental concept is applied in the industries